Hello, everybody, and welcome to this week's Astro Coffee Hangout. My name is Tony Darnell, and I work at deepastronomy.com, and we have another, as we always do, really interesting hangout planned for you today. We're going to be talking about exoplanets, and in particular, the exoplanet known as 51 Pegasi b, which is also called 51 Peg b, I guess, for short. And there has been a paper that has recently come out that I think it was back in February, if I'm not mistaken, that we're going to be discussing today. Now, I put the link to the, I think it's the phys.org website on the description box. So if you want to follow along at what we're doing, and that's what we're talking about today. And we're going to get started. But before I do, I want to introduce my co-host, Dr. Carol Christian. She is in the lovely city of Venice, and she is going to tell us a little bit about these hangouts. Hi, Carol. It's good to see you again.
Hi, nice to see you. Yes. So Afternoon Astronomy Coffee was born out of the idea that lots of times, at least in astronomy, we have astronomy coffee or science coffee in our departments and research organizations. And we talk about research that we've read, among other things. And the idea is it would be fun to invite other people into this conversation. But instead of talking among ourselves about somebody else's research, we thought, oh, what we would do is talk among ourselves and invite researchers in and ask them directly rather than speculating on what they were thinking, what they did, how they arrived at their research results, what the data was like, and what they're going to do next. So that's the idea behind Afternoon Astronomy Coffee. It's informal, nice, informal, relaxed chat with our researchers.
Yeah,
and I wanted to mention that we are supported by the American Astronomical Society and the American Aeronautical Society to do these hangouts.
Astronautical, and yes, that's right. And while the views and opinions, while the hangouts are endorsed by those organizations, the views and opinions are not necessarily endorsed. So let's go ahead and get started. I want you guys to join our conversation already. I'm seeing a lot of people. There's 3 ways you can interact with us. There is the YouTube live chat. There is deepastronomy.com/live. And there is a the Twitter hashtag AstroCoffee, and I'm already seeing a lot of people. Andrew Planet is on deepastronomy.com/live, and he's saying, are we doing these hangouts an hour earlier each time on a permanent basis? No, Andrew, but it's just the difference in time, and the reason it's earlier for you is that you guys haven't switched your clocks ahead yet in Europe, and we have already here in the US, so there's a bit of an hour difference than when we usually have them. But as soon as you correct your clocks, we'll be right back, because right now I think you're 4 hours ahead. We used to be 5, so there you go. Also, we got lots of people joining us on Twitter. I'm sorry, on the live chat. So please ask your questions and get your comments there. So many of you are already here. Adam Synergy is already commenting. I've heard of today's guests. 51 Peg b is not the first exoplanet these guys have studied. That's right, Adam. Okay, then let me introduce them. So with me are the authors of a paper that we're going to be discussing today about the water vapor, I believe they found in the atmosphere of 51 Peg b. And joining me is Dr. Jane Birkby. She is a NASA Sagan Fellow at the Harvard-Smithsonian Center for Astrophysics. She got her PhD in Cambridge and is with us today. And she is also the lead author of the paper I think we're looking at. So welcome, Jane.
Hi, good to be here.
Thank you. Thank you for joining us. Also joining me is Dr. Matteo Broghi. He's a Hubble Fellow at my old stomping grounds, University of Colorado. Yes, he's there today and the Boulder campus. Welcome, Matteo. Thanks for representing a very fine organization. He is at the Astronomy and Planetary Science Department there, and he models, or at least he said he was being humble and saying he runs other people's models, but he's a modeler and looks at planetary atmospheres. And finally, joining me from the Netherlands is Dr. Remco de Kock. He's at the Netherlands Institute for Space Research, and he works with other scientists, and he's also a modeler of atmospheres of planets. So welcome, Remco. It's good to have you with us.
Good deal.
Yeah, okay, so we'll get started. The exoplanet we're talking about is 51 Pegasi b, and I want to kind of set the stage for us a little bit. Jane, could you, on what this planet is, how far away is it, and where is it, and all that kind of stuff?
Sure. So 51 Peg b was the first exoplanet to be discovered orbiting a main sequence star, so sort of a regular star like the Sun. And in fact, actually, its host star is very similar to our own Sun as well. But the and so it's at about 50 light years away, the constellation of Pegasus. And it was discovered it was announced in 1995 by Michel Mayor and Didier Queloz, and then also confirmed by Jeff Marcy and Paul Butler as well, all around the same time. So it was really the sort of first planet we'd found around sort of what we consider a normal star. But there was a lot of controversy about it at the time. People didn't know that it really was truly a planet. So I can talk a little bit about the methods later on as to how they actually found it.
We'll do that.
Yeah, so it's sort of historically sort of a important planet, sort of the mother of exoplanets. But it was very, I can talk a bit more about the planet itself. It was very unusual. So it's nothing like Earth. It has about the same size and mass as Jupiter, which was sort of the original discovery information. But its orbital period, so the length of a 51 Peg-B year, is very short. It's only about 4 days. So it's whizzing around its star very rapidly. And up until that point, theorists didn't really think that planets could form that close to their stars. It's too hot for them to form there. And so it sort of brought in this idea that planets form further out and somehow migrate inwards, and sort of generated this whole field of planet migration and scattering and how they move around in their disks.
Now, it's classified as a hot Jupiter, right? That means it's so. Tell us a little bit about that type of exoplanet.
So yeah, hot Jupiters is this class, so 51 Peg-B being the sort of progenitor of that class of exoplanets. So they're about the same size and mass as Jupiter, but because they orbit so close, they're all within sort of, let's say, less than a 10-day orbit. Their temperatures are sort of between 1,000 and 2,000 degrees, so extremely hot. And this can lead to
being the size of Jupiter isn't enough. It also has to have this really short year of only about 10 days to be classified as a hot Jupiter.
Okay,
so
they have to be hot, and the reason they're hot is because they're close to their parents.
So that
but wait a minute, Carol. Couldn't they also be brown dwarfs and be hot that way?
I don't know.
See. Okay, so
I don't know. Jane can answer that. But I just wanted to point out that, as I have pointed out in these Hangouts before, astronomers are not very subtle with how they name things.
Or imaginative either. Okay. All right. So we've got a star roughly the size of our sun, about almost identical to our sun. We've got this planet so close. It's the size of Jupiter and so close it's going around in about 4 days. And so this is a strange situation anyway. How common, maybe I'll have you comment on this, Remco, how common is this kind of scenario out there? How many of these Jupiters would there be?
Well, these type of planets are the first ones that we found a lot of, but actually they're less common than Earth-like planets. As we found out, for instance, the Kepler mission later on found that almost all stars on average have rocky Earth-sized planets, and less systems have these hot Jupiter types. But the hot Jupiters are easier to find, and so we found them first. And they're also easier to study their atmospheres because they're hot and big, which makes them easier to see.
Yeah, so there's sort of a bias there, isn't there? When you've got a large planet circling a star, it makes it a little bit easier to see than if you're trying to find Earth-like planets. So how was this star detected, Jane? You want to comment on that a little bit? And while you're out there, I'm going to go ahead and share my screen.
Okay. So the way they found the planet was using the Doppler wobble method, or the radial velocity technique, as it's called. And so you can see in the video here, this is showing the planet orbiting the star, and obviously the star and the planet are not to scale. But what you're seeing in the bottom bit is the spectrum. And so the dark lines that you're seeing are caused by molecules in the the star's atmosphere that absorb certain wavelengths of light, so they absorb certain colors. But then as the star and planet orbit, you'll see that it's not the planet that's going around the star, it's actually that both the star and the planet are orbiting a common center of mass. So the star is in an orbit, it's just a very small orbit and quite slow. And so what happens is, as the star moves towards us at the moment, and then eventually it'll come around and it'll move away from us, as it moves away, the light, the absorption features shift towards the red end of the spectrum, and then as it comes towards us, they shift to the blue. And so we can measure this change in the positions of those absorption lines. And in doing that, we're able to measure how much the star is actually wobbling. And then just using Kepler's laws of motion, we can figure out that there must be another body in the system that's causing the star to move. And we can then get, from this point of view, a minimum mass for the planet. And the reason that it's a minimum mass is that we don't know necessarily beforehand what the inclination of the system is. So right now, as the planet comes towards us, we see this is pretty much edge on, so that full force of that velocity is coming towards us. But you can imagine if this system was actually tilted, so it was completely face onto us, we wouldn't see the planet changing in velocity at all, because it would just be going around in a circle like this and not forwards and back. So what is the best what I like about the radial velocity method versus, say, the transit method, which measures tiny dips in brightness and to detect a star, is that you can get different information about it, but it isn't so line of sight dependent, is it? As would the transit method be. So is there an optimal orientation that you like to see these at, like tilted? Like you could still see it, right? You know, if you were looking down over the top of the plane of the orbit, right? So if you were exactly looking down on it and there was no motion of the planet towards or away from you, then you wouldn't be able to detect it. But as you start to tilt the system, sorry, I'm showing like this. So yeah, if it's completely face on and the planet's just going around and around like this, it's not coming towards or away from you. But as you start to tilt, then the planet starts to do a forwards and back motion. And that forward and back is what you need to see, because you need to see those lines shift, red and blue. So I don't know what the minimum inclination is. It's been detected, and we only know that for a very few planets for part of the work that we've done. So certainly at 45 degrees, we detect these. And yeah, you can go lower, and then it depends on the sensitivity of your instruments. Okay,
so and this was discovered, when did you say it was discovered?
It was announced in 1995.
So now this is quite a while back then. This is pretty one of the first ones that we've seen, isn't it? Yeah, okay.
Yeah, it's well, it came of age last year, so 21 years old.
Okay, Matteo, let me get you in on this a little bit. Tell us a little bit about what your interest is in this system and some of the work that you're doing.
Yeah, so my interest actually goes back to 2013, when I first tried to observe this planet with a very similar method, and actually with the same instrument that we use for this water detection. And the puzzling aspect about the study is that we had 3 different observations of the planet taken at three different times, and in 2 of them we were seeing a signal from the planet, but in 1 of them the signal completely disappeared. So applying scientific method, we were a little bit puzzled by this. We tried to explain that based on the observing conditions, etc. But we could not find any reasonable explanation why the planet wasn't detected on the 3rd night. So we call it a tentative detection. So we were very cautious on saying we actually saw the atmosphere of this planet. And we had to wait, actually, when we repeated the analysis like recently, and we finally detected water to not only to confirm what was seen in 2013, the 2 measurements are actually perfectly consistent within each other, but also, of course, to focus more on water vapor, whereas like back in 2013, our main focus was finding carbon monoxide. And this depends, we were looking at certain frequencies in which we were expecting to see carbon monoxide, but we were not conversely expecting to see much water. So this is why my interest was suddenly refreshed by these new observations. And when we finally got detection of water, it also makes me feel much more comfortable that a few years later, this result that I found was actually confirmed.
Oh, good. Well, let's talk about the water detection then, Jane, a little bit. Tell us, Matteo's given us a brief outline about some of that it was detected in, I think he said 3 different instruments. Tell us about the observations and the detection itself. What did you use, and what, this was with a spectrograph, I assume, too, right?
Yeah, so this is a technique that hasn't been around for so long. The very first use of it was in 2010, that actually showed a signal. And that was by E.S. Snullen and the group in Leiden, which is where the 3 of us actually met. And so it's a lot of atmospheric characterization has been done using transiting planets, but 51 Peg-B is a non-transiting planet, so we needed a different way to do this. So actually, if we could go back to your video of the radial velocity technique.
I will do that. Hang on.
So that if it's not transiting, that tells you just a tiny bit about the inclination then, right?
Yeah, so it sort of rules out things 85 degrees.
Edge on.
Yeah. Okay, so if I go back to this video. So when I showed this video, I said the way they detected it was they measured the movement of the star, and it's very small. The velocity there is only of order, a few tens to hundreds of meters per second in terms of velocity of how fast it's moving. However, the planet is whizzing around extremely fast, and on the order of 100 of kilometers per second. So it's a factor of 1,000 times faster that it's moving. And so we can actually use that information. We can actually use that velocity change over the course of our observations, which took about 5 hours, 4 to 5 hours for this work. So for our purposes, the lines of the star aren't actually moving that much, but the planet lines, the absorption lines, are moving a lot over the course of about 5 hours. And so what that does is it allows us to pull out the planet. And the reason we can't just do that directly is that the planet is about 10,000 times fainter than the star itself. And so it's very hard to see. It's the equivalent of trying to see a firefly next to a lighthouse lamp. And so in this case, we have that faint light, but we also have now our little fireflies moving. And so it's an extra piece of information that we can use to track where its light is going. So that was sort of the method that we used to do this.
Okay, hang on just a second, Jane. So I've seen this animation about 1 million times, and I never really thought much about which lines we're actually looking at. I know this is a simplified diagram, but the planets aren't to scale. But what lines are we actually looking at here then? What's actually moving back and forth? Is it the star? Is it the planet? Or is it some combination of both? Yeah,
so what you're seeing here in this sort of artist video, what they're showing are the lines of the star. So you'll see that as the star moves away from us, they're redshifting.
Okay, good. So it's a star.
Yeah, so and what you would see if the planet was extremely bright, and say if the planet was as bright as the star, you would see 2 sets of lines. And
so right here, I've just paused it right here. The planet's pretty bright.
Here it is. This is an artist conception.
I know. But would this be the spot where it would be the brightest? It's also really close to the star. Would you see more spectral lines here in this part of its orbit?
Yeah, so you would actually see, what you can see is actually as it comes around the other side, so it shows its night side, and then it moves around and it shows its day side. Right. And they're actually 2, in terms of chemistry, they're 2 very different things. And so we get different features in the spectrum of the planet depending on where it is in its orbit. But yeah, if both the star and the planet were the same brightness, you would get 2 sets of lines. And one would be moving towards the red as the other was moving towards the blue. And then they would come back and swap over as they went through the orbit.
Okay.
And so the problem we have is that they aren't the same brightness, and the planet is 10,000 times fainter. And so that the sort of the lines from the planet itself are buried way down in the noise from from the observations. So they're completely dominated by the star.
Okay, can you give us some sense what that might look like, the data from that, or was that what that graph was you were showing us before we started, or was that something else?
Yeah, sure. So I can let me bring that up.
And while she's bringing that up, Remco, tell us a little bit about what your thoughts are on this system, this discovery or this detection of the water vapor in the atmosphere.
So these hot Jupiters are hot, and the Jupiters means that they're mainly composed of hydrogen, like Jupiter and like stars, basically. So we kind of, in that kind of hot regime, you expect things like carbon monoxide and water to be there as a vapor in the atmosphere. So the presence of these water vapor is not very surprising, but it is a first step that we can actually detect it. And if we keep improving our method, we can actually derive something about the exact abundances of water. And then if you compare this, for instance, with the abundance of carbon monoxide, you can start to say something about, for instance, the formation of the planet. So how many oxygen atoms versus how many carbon atoms are there in the planet? And that's saying something about how this planet is formed. And so, yeah.
Okay, good.
Yeah.
Okay, well, let me go over here to Jane then. So I've got your graph up.
Yeah.
And this goes on to what Matteo was saying about carbon monoxide, it looks like.
Yeah, so here, well, Matteo can say if he wants, but this is just, it's an example. So here we're using carbon monoxide rather than water.
Mm-hmm.
So what you can see, the main sort of graphic in the middle, again, is very similar to that video that we just looked at.
Mm-hmm.
So here we have, you can see our planet is going around at kilometers per second. You can see it's day side, and then you can see it comes around and we see it's night side. So one of the key points about the technique that we used very high resolution spectroscopy. And the reason for that is the following. If you look at the bottom graph here, this is showing the spectrum, so those absorption lines, for the carbon monoxide molecule at very high resolution. And you can see that it forms this band of very dense, strong absorption lines. If you go to lower resolution, so if you try to use a spectrograph on, say, the Hubble Space Telescope to do this, all of these lines would be basically convolved down. And at low resolution, this would just be a singular shallow line, like a singular shallow deep, broad but not deep feature. So you get one line.
You wouldn't see the little detail of lines in there if it were low resolution.
No, you would just see one sort of very broad feature. Whereas when we go to high resolution, and for this we use the CRIRES spectrograph on the Very Large Telescope, which is down in Chile. At high resolution, this is around 100,000, you see where we get this dense forest of individual lines. And what's key for this is that every single molecule has its own unique pattern of lines. So water looks very different to this. I can potentially even show you what the other molecules look like. Yeah, so if I show you here.
Oh my gosh.
Oh, 1 second. Move that down. There we go. So here's our CO. And you can see that oxygen itself, again, we have these relatively well-behaved lines. But then for methane, carbon dioxide, and water, you see there's many more lines, but it's very dense, very complicated spectrum. And this actually makes it harder to measure the exact positions of these lines as well. But if I take us back to our other plot that I've now lost. Yeah. So the goal is at high resolution, what we can actually do is trace out what happens to each and every single line over the course of the planet's orbit. And so that's what's showing here on the right. So you see each of the white lines, which represents one line in the planet's spectrum. You can see it traces out this sinusoid curve over the course of the planet's orbit. Whereas if you look at the what I've labeled here as the telluric line, so this is contamination from the Earth. You can see that this doesn't change its position in wavelength over time. And so that means we can remove everything that's not moving in time, and then that just leaves us with the things that are moving, which is the planet signal.
Nice. That's really cool. Okay. Okay. Well, so when you guys are, we got a couple of modelers here, so I want to get you guys in on this. So let's talk about, what do you guys do with this stuff? You guys get these observations, and by the way, I think Jane, you use it's called the cryogenic high resolution infrared Echelle spectrograph at the Very Large Telescope in Chile. Correct?
Yeah.
That's what okay. So what do you guys who model, and I'll let either Matteo or Remco go on this one. What do you guys like use this as inputs for your model to go, okay, well, if we've got these kinds of abundances of different things in the atmosphere, then the planet must have formed the following way? Or what do you guys do with this information? Give us some insight on what modelers do.
So
maybe both of you. I'll start with you, Remco, and then I'll go and have Matteo comment.
Yeah. So Matteo has done actually a lot of the observing and data analysis start, and only recently starting with the modeling. But
I see. Okay, well, I'll ask him a data analysis question. Then just
So, eventually you want to do that, but these methods is very new still, and we're already happy that we are finding something. So our first goal was basically trying to find something. And for this, we just calculated a lot of different spectra for lots of different compositions of the atmosphere, and basically try to match them with the data. And basically for the data we have, it doesn't really matter that much which composition you have, as long as there is water in it. So we don't yet have the good sensitivity, so the good enough measurements to detect really detailed information about the atmosphere. But we do know that there's definitely water vapor in there.
Okay, and so Matteo, you get this data from so Jane goes down to Chile. She gets this data, and then what happens? It's actually like sometimes we all three went at some point. Oh, you all went. Okay.
Observing on the telescope. So it's just like sometimes it's one person, sometimes it's another person. So we go down to the telescope, we get the data. Normally what happens on a typical night, if you are not too tired or too much sick because of the altitude, you are trying to do some very quick data analysis to see if the quality is right. And then we start by using this process that Jane described. So this intrinsic difference between what is produced in the Earth atmosphere and what is produced in the planet atmosphere. We start processing the data and arrive to a stage in which we can compare our processed data with the models that Remco is computing, and that is done through a process that is called cross correlation. And basically, what this cross correlation does, it tries to match the model that we have that is produced by Remco with the actual data. And in this way, it combines the tiny signal of each one of those molecular lines that you were seeing in the plot that Jane showed into a collective signal, therefore amplifying the signal that would be very, very small, as Jane mentioned before, and allowing us to detect that. And then maybe I have, let me see if I can share my screen. I can show you something regarding that. Let me see. Yes. I don't know if you can see my screen here.
Yep, we can see.
Basically, what we have is in the stop panel. We have basically noise, which is, you can imagine that this is the final stage before comparing the data to the models. And if you really squint your eyes, you can see the very tiny signature. This is an artificial signal that I injected on top of that. There's a lot of slanted lines there, but it would be impossible to detect this as it is. So based on the models that Remco produces, we can use this cross correlation to pass from the above plot to the plot below, in which you see all the signal, all the tiny signal has been combined, and now the signal from the planet appears as a very clear stripe in the dark stripe in this data. This is essentially what we do. We repeat that for many different models. We test many different radial velocity for the planets, and then therefore this is the way we can derive both the motion of the planet and therefore its mass and orbital inclination, and which species are present in the atmosphere.
Okay, hang on. So I'm looking at this this dark line going sort of diagonal down this bottom frame that you've got there. You're getting all this information like velocity and mass and composition of the atmosphere.
Yeah.
That.
Yeah. So the key here is the strength that you get from, so how dark is that stripe, and the slope that that stripe has, because the slope tells you how the velocity of the planet with respect to the observer is changing in time. That in turn reflects how the planet is moving along the orbit. So you can invert that, and from that derive what is the orbital velocity of the planet as seen from the Earth, which is therefore projected on the plane of the sky, and therefore derive the orbital inclination.
So
and
just a slant of that line tells you the speed.
Yeah. So what I canceled before is there's this guiding lines here. So if you're observing a non-transiting planet, you do not know a priori which is the slope of this line. So you actually have to try all possible different slopes for that, and then like coed sum this dark stripe along all these different slopes. And if you do that, I hope this is not too much confusing, but you get this kind of diagrams. Let's just focus on the part on the left. So this is the strength of our signal that we measure from the planet. And on the two axes, you have how the planet moves compared to the observer. So on the x-axis, you have the global velocity of the system compared to the observer. And on the vertical, you have how fast the planet is moving along the center of mass of the system. So that's enough, since we also know how fast the star is moving around the center of mass of the system. That's enough to derive the planet mass and the orbital inclination of the system.
We've talked about it so many times on these Hangouts. I've never actually seen it. That's really amazing. I love that. Okay, so the brightness is your signal strength. Along the bottom is the velocity of the entire system, you said? The star and the planet. And the y-axis was just the planet.
It's just the planet component, which also tells you see, by the fact that here...
Oh, go ahead. I'm sorry.
No, sorry. This is also a confirmation. You know that something is moving, in this case, 110 kilometers per second. This is not 51 peg, but we produce very similar plots for 51 peg. And now if you know that the star is moving with an amplitude that is 1,000 times smaller, there must be a mass ratio of 1,000 between the planet and the star. And this is how you weight the planet compared to the star, essentially. And then sorry, just to conclude, and then the strength of the signal, which is how intense this blob is here in this plot, repeated for different models, for different sets of models containing different molecules in different ratios, tells you something about the properties of the atmosphere. So this is how you also infer if a model, if a particular set of model fits better the data, or vice versa if it doesn't.
Yeah, wow, that's a lot of information in that graphic. Thank you very much. That's really cool. Okay, I'm going to get to a few comments here because they're backing up, and I want to get to some of them. Adam Synergy, hi, hello, John. Hi, guys. Oh, John Suffol's here. It's good to see you too. Not too bad in Hull. Hoping to get the scope out later tonight. Well, I've always wondered about you guys. I lived in the UK for a year, and I've always been amazed at just how much observing can get done. You always think of it as cloudy and foggy all the time, so it's really great that you guys are such a robust amateur astronomy community. I was in Kielder, by the way, up in Scotland, and that they have an amazing telescope up there too. Okay, so let's get to a couple of questions. Awesome that the astrological societies are supporting. No, there's a difference. Okay, it's not astrological society. Swiss Galaxia, it's good to see you're back. Good to see you again. Hi from Finland. Dutch represent. Yes, of course. Is it a hot Jupiter? Yes, it is. We were just talking about what a hot Jupiter is. It's not just a planet that is the size of Jupiter, roughly. It also has to be very close to its star And Carol tried to tell me it couldn't be a brown dwarf or anything, to be too hot, but it's got to be close to the star to be hot. So let's see. Tony, can I put it on full? Okay. Where is it? So Desert Mouse is asking, so there is visual confirmation. Have we seen this exoplanet yet? I mean, in other ways besides with spectra?
So we haven't seen this by what we would call direct imaging, and that's because it's extremely close to its star. So we actually calculated this in the paper, that the planet is actually 3 milliarc seconds projection on the sky separated from its host star. And at the moment, the closest thing I think that's been resolved in actual as images is sort of around the 0.1 arc seconds. So it's a factor of 100 times closer than the closest thing we've seen to its star.
Yeah.
So we call that out spectrally. So this is a direct detection of this planet. We're not inferring it from what the star is doing. It's a direct detection, but we do it spectrally rather than in imaging.
That's great. Okay. And Galaxia is asking, I wonder how many other planets are in this system, and if any of them are in a habitable zone. What type of star is this? We mentioned this earlier, Galaxia. The type is a main sequence star, just like very similar to our sun. What about other planets, though, guys? Anything else in the system?
So, yeah, I can talk briefly about this.
Okay.
So we mentioned earlier that we think these hot Jupiters form quite far out, and they migrate in over time. And it's not completely clear yet what that migration does to any other planets that may have formed closer in, say, within the habitable zone. So as these massive planets come in, they tend to scatter and disrupt other planets that are there. And the same thing happened in our own solar system. Jupiter and Saturn moved, and they scattered out the Oort cloud, and so our solar system didn't start the way we see it today. And so this potentially, so if you have a migrating hot Jupiter, that potentially it can completely scatter and destroy any other planet formation that's happening. However, there have been a few systems, I think WASP 47 is an example, of where there's sort of a small planet and a very close-in giant planet, and then two smaller planets further out again, and then another giant planet way further out. So they can survive in some cases, but we think that perhaps the migration causes most things in the habitable zone probably to be scattered. I don't know if Remco and Matteo have anything to add.
I agree.
I had a question back to the spectrum modeling. I understand that you're comparing model spectra to what's detected, and I assume, and so it's a question, if you just had one molecule, you could still determine these velocities. But in fact, it's not just the velocities and getting the relative velocity of the star and the other object. You've actually matched the lines for many molecules. Right, and so it's not just that one of these matched, it's many, and you actually have a probe of the composition of the atmosphere. Is that right?
Yeah. So, well, yeah, but yeah, Remco, go
Remco should go ahead with this.
No, so for this paper, we only detected water using that data, but that doesn't mean there aren't other molecules. But the water has many thousands of lines. So we detect the combined effect of all these different lines. So Matteo's earlier paper showed there was probably carbon monoxide as well. So we now know that there's at least carbon monoxide in water. But yeah, for the other molecules, we haven't detected them yet, but that's also probably because simply the data is not good enough yet.
Yeah. So water and carbon monoxide are sort of the two main molecules that we expect to find in these particular types of planets, these hot Jupiters. And so there are probably other molecules there, but they are much lower abundance. It makes their signal harder to detect.
Okay.
Okay, Matteo, do you want to add anything?
No, I agree with them. It's really, even though we detected just one molecule, as Remco said, the strength is that we are combining these hundreds or thousands of lines. So the chance of having a detection from by random is extremely unlikely. So we really combine with this fact that we combine and we match line by line. We can have quite an unambiguous detection of these molecular species, which is really powerful, because water is one of the main species we want to look at, not only for these giant planets, but in the future also for smaller planets. So being able to detect water at with high confidence, and it's one of the first steps towards more temperate planets.
That's right. Yeah, we got to get that down first, I guess. So let me just take a minute and remind everybody, you are watching an afternoon astronomy coffee hangout with Tony Darnell and Carol Christian. And today we are talking about water vapor detection on the hot Jupiter known as 51 Pegasi, which is an exoplanet orbiting a star very similar to our sun. My guests are Dr. Jane Birkby. She's a NASA Sagan Fellow from Harvard-Smithsonian Center for Astrophysics. Also with me is Dr. Remco Dukak. He's from the Netherlands Institute for Space Research. Also, Dr. Matteo Broggi, he's a Hubble Fellow at the University of Colorado Astronomy and Planetary Science Department, and we are talking about their paper that came out earlier last month about this detection of water vapor. And as you were just saying, Matteo, this water detection is something that we can extend to other things, and I guess I'm curious about what other, and to get to a comment that was also made by Adam Senergy, he's asking, will further observations allow different molecules to be detected? Can you guys comment on that a little bit and maybe talk about the future of your research? If you did more observations, would you see other things? And looking ahead.
Remco, do you want to comment on this, since you were already introducing the topic of other molecules?
But the short answer is yes. But maybe you can do the long answer.
No.
So more observations will show other detections.
Yeah, and the exciting thing is also, for one, there's a lot of new instruments that can do these type of measurements at very high sensitivity. So really well. That allows us also to do these type of measurements also over a really broad wavelength range. So now we had these snapshots of light, basically, of wavelength frequency, and that allowed us only to look at one molecule at a time. But these new instruments we can look at many different molecules at the same time, and we will probably detect different molecules at the same time. But in the further future, there will be larger telescopes, and this will be, for instance, the Extremely Large Telescope in Europe and the GMT, Giant Magellan Telescope. Yeah, from the US sides, that will be much larger than any telescope before, and that will greatly help especially this kind of measurements. We can do detect a lot of molecules in this kind of planets, but we can even go to much smaller and cooler planets with these big telescopes. So maybe, both Matteo and Jane have done studies on these future telescopes, so maybe they can have a bit more information about that.
Any comment, guys?
Yeah, so I think that's one of the single most exciting things about this technique is that with the next generation of the Extremely Large Telescope, so the European Extremely Large Telescope, which is a 39-meter mirror, and the Giant Magellan Telescope, which is a 25-meter mirror, and then the TMT, which will be a 30-meter mirror. We can do everything we're doing now, but for the smaller, cooler planets, we can also be time-resolved and three-dimensional studies of the atmospheres. And I think the real driving goal for us is to find what we call the biomarkers. So looking for these signatures of life on other Earth-like planets out there in our local neighborhood. So looking for not only water, but oxygen and ozone as a sort of marker of oxygen, and methane as well. And we think in combination, those four molecules would be the sort of smoking gun of life on another planet. And we're not really talking about SETI type life. We're not talking about advanced civilizations. We're just talking about little microbes maybe hanging out in the oceans and on the surface, and giving off enough of these gases that we can actually detect them in the atmosphere. And so we've done simulations for mostly for the EELT at the moment, and for how long it would take us, for example, to see oxygen in the atmosphere of an Earth-like planet transiting what we call a mid-M dwarf, so a star that's about a quarter of the mass and the size of the sun. And because these planets are, the stars, sorry, are much cooler, their habitable zones are much closer in, so it's only on the order of sort of 11 or 12 days. And so we think with the ELT, we could get a significant, like unambiguous, significant detection of oxygen if the planet had it, with something like observing 14 transits in this case. But it would take on the order of 5 to up to 20 years, depending on how much noise there is in the data. But that would be a completely robust and unambiguous detection. So that means within our lifetimes, we may actually be able to say that there is life on other planets out there.
I don't care who you are, folks. That is exciting news. That I forget alien civilizations. I would be happy if we could find the microbes, the gases from the possibilities of life on other planets would be huge. That would be enough for me. I think that would be the most important discovery, I think, ever, if we could get that.
So we have 2 targets already that we're going to be aiming for this. So the one is the Proxima b, which was announced in August last year.
Yep.
So this is our very nearest exoplanet, and it's orbiting Proxima Centauri, which is a small red star. And then the other sort of main target for this kind of work at the moment is the TRAPPIST-1 system, which was also announced recently. This 7 planets orbiting a small star about 30 or 40 light years away. But what's interesting to sort of realize about this is that there are another over 200 small stars that are closer to us than the TRAPPIST-1 system, but they don't necessarily have transiting planets. They don't necessarily have that favorable alignment.
That's right. That just happened to be a nicely aligned system for us.
Yeah. Yeah. So what's great, I think, about this particular technique that we've used is because we don't need the planet to transit, it means that we have access to all of those stars in our local neighborhood, say within 30 light years, that we can actually do this analysis for. So we really can actually go and look at all of them rather than just those favorable few with transits.
That's right. It always comes down to size, folks. If we get large enough telescopes to resolve these smaller planets and stars, that would be huge. And we got the very large telescope. This is going back to Carol's point about how astronomers name things. We've got the very large telescope, which imagine it's very, very large.
Right. The giant Magellan telescope.
The extremely large telescope, which I guess would put the very large telescope to shame. Then we got these other ones, 30-meter telescope, Magellan telescope. I'm waiting for the super, ultra, mega big telescope. That's what I'm waiting for.
I think this is proof of the poor long-term planning of mankind. They can only see like 15 years ahead of them.
Right. Okay. So come, Hans Milling, better late than never. Yes. Thank you for joining us. It's good to have you back. Vatso Panwar, I don't know how to ask your question. I'm going to read it, but I don't understand it. If our guests understand it, I'll let them answer it. But I may ask you to retype that. For RV search of the face-on orbit, the inclination will be 0, and the minimum mass, which is m sine I, will drop to 0. Right? I don't understand that question. I can have him re-ask.
Yeah.
Okay.
Yes,
I'm
sort
sorry,
of.
I don't understand that question.
The answer is yes,
it's
sort
correct.
of.
It's correct.
Correct.
Yeah, it basically means there's no constraint on the mass.
All right.
Okay.
Yeah.
Bahez Ahmed from YouTube is asking, would ALMA, the Atacama Large Millimeter Submillimeter Array, be able to study this further? Could we get radio observations to help out with anything? Would that help us? Tell us anything.
Well, maybe
There's a lot of silence.
So, with radio, so stars and peak their radiation mainly peaks in visible light, and planets the most of the radiation is emitted in infrared light, and radio wavelength is even longer wavelength, which means there's a lot less radiation from the planet coming towards us. And so this ALMA telescope has a huge surface area. So it's, in terms of surface area, it's a lot bigger than the very large telescope. But it also has to do with the very much less signal from the planet. And also, these telescopes can only see one of these absorption lines at the same time, or only a few. And whereas we in infrared, we have thousands of lines where we can combine the signal to make it stronger. So you have a weak signal from the planet, and you can only look at a few lines, which makes it really hard to do this with the radio.
Okay. Right. Yeah, Alma was recently brought to my attention because I'm doing a story on the Event Horizon Telescope, and that's an extremely valuable telescope for studying things in the radio, but I don't know that it's really going to do much in this particular case. Philip W. is asking, question for the team. In the animation of 51 Peg B's transit, the star seems to wobble. I guess he's referring to that ESO animation we were showing about the transit method, which we already said was exaggerated. Could another planet be in the orbit of the star inside the wobble area? That's a new term. Or would it be too hot to be in there? You know how we saw the star wobbling and it made that little circle? Could something be in there?
So I think that video is really very much exaggerated. Most of the center of mass point is probably inside the star. And so it's probably, even as it does wobble around, anything within that orbit would be inside the star, I think. So it would just be obliterated. Okay.
So let's see. Hope we get it. So Battle Bunny. Battle Bunny. I like that. He's asking, I hope we get an answer. Now I want to know too. Which question was that in reference to? But if I haven't asked it, here's Jason Spinelli. Let me ask this one. If it was a neutron star, the star we're talking about, 51 Peg, it wouldn't have been accurate to the computer model, at least for a split. Oh, that's not a question. It's just a comment. At least for a split second before flying into a massive neutronium explosion. Where? What?
What? If it was a neutron star, we would have never seen the lines moving back and forth because it wouldn't have an atmosphere. So it wouldn't have even been discovered. I did have a question, though. Is it true that 51 Peg B is tidally locked? And does that have anything... First, is it tidally locked? And does that have anything to complicate the observations or not?
So Matteo has done some research into tidal locking, and if you want to talk about that.
So I think from theories, we would expect these hot Jupiters to become tidally locked on a very short time scale, definitely much shorter than the age of the system that we see today, that is probably a few giga-years old. We do not have yet a direct evidence of this. One way of actually seeing that, so tidally locked would mean that the orbit of the planet is on the same time scale as the rotation of the planet. And we know when a planet rotates, what would happen basically that instead of having in the spectrum very narrow lines, these lines from the planet atmosphere will broaden and broaden and broaden. Now, the degree of broadening is, of course, related to the speed of rotation of this planet. So one might imagine, as we did, as our team did this for another hot Jupiter, to get very carefully to study the shape of these spectral lines, and from the broadening to derive the rotational rate of the period. Therefore, either confirming or not confirming the tidal lock. Now, we are still probably a little bit on the low signal to noise, so we need probably a little bit more observations to do this. But it is technically feasible with this technique also to confirm the tidal locking for these giant planets. Yes.
Okay, good. Now I want to get to a couple more. Running out of time. I want to make sure I get them all in. Let's see. Patrick DeMarta is saying, Tony, broghi in Italian sounds like broghi, but you pronounce it like it was broghi. So was I saying your name wrong, Matteo?
It's fine. It's
okay.
Everyone. It's broghi.
Oh, sorry.
But everyone outside of it.
Sorry. Yeah,
but I kind of adopted a new last name after I left Italy, so that's okay.
So is it an American thing? We always mess that up. So yeah, sorry, broghi.
No problem.
Okay. Let's see. Hans Milling is asking, will Jupiter also travel closer to our sun and swallow Earth or send Earth to a different orbit? This goes back to your comment where you guys were saying you believe these hot Jupiters form farther out. Will this happen to our planet, to our Jupiter?
So I think for the sort of very long term, Jupiter is probably going to stay more or less where it is. But I think as the sun starts to age and expand, as it does, I think that will probably affect the orbits of many of the planets. So the sun will sort of expand out, and it'll almost touch the surface of the Earth. So we get like the scorched Earth effect from the sun, and then that must in some ways probably end up affecting Jupiter. I don't know if any of the others want to comment.
No, I think in this context, like what we refer to is this migration that happens very early in the history of the system. Essentially, when there's the protoplanetary disk from which the planet are born, essentially when a gas is still present, we're talking about, we don't know exactly the time scales, but we are talking about the very early stages of the life of these systems. Our solar system is very much evolved. So we have, I think, we can safely exclude that a process like that would happen at the current stage of the solar system. As Jane was mentioning, there might be other events in the more long-term history of the solar system.
About 5 billion years.
Yeah, producing the same thing.
Okay. Philip W's got a great question. Question for the panel. Is there a theoretical distance limit to how far spectroscopy can be used to analyze molecules from a planet? That's a good question. Is there a limit to how far out you can go with this?
That's a good question.
Depends on the size of your telescope, I guess.
What'd you say?
So if you can build a telescope in space that's hundreds of kilometers big, I don't see why you can't do it for another galaxy.
Yeah.
I guess.
So there's a limitation with this particular method we used here. We use the velocity change. So the further and further out the planets are, the slower they're moving. And so at some point, they're not moving enough over the course of, say, a night for us to actually be able to separate them from things that aren't moving, like our own Earth's contamination, like those telluric lines that I showed. So, but then we have sort of another technique where we actually use the spatial information instead of the velocity information to pull out the planet instead. And so that's work actually by Henrietta Schwartz, who's unfortunately couldn't join us today. She's speaking at MIT. So it's still using high resolution spectroscopy, but using the spatial information rather than the velocity information to pull that out. And so we sort of come at it from two ends. So we can do the close-in things with velocity and then the far-out things with the spatial information. So in principle, if you have a big enough telescope with enough signal to noise, that you can actually probe pretty much all separations.
Wow, that's amazing.
And people do this for like stars around black holes as well. A similar method.
Okay.
So,
well, he has a follow-up question. He goes, if there is a limit, then is there a red line area where you wouldn't trust implicitly the results? So you're saying that with this particular method there are limits. Where would you stop trusting what you're seeing? At what point?
In terms of distance? Or?
Yeah. Mm-hmm. I think so. I think it's what you meant, right, Philip? So yeah, I think it's in terms of distance.
So I guess at some point, I wouldn't necessarily say it's the technique that would fail, but if you go too far away from the star, that the thing you're seeing is no longer gravitationally bound to the star itself. And so then you wouldn't know whether it was actually associated with that system or not.
Okay.
The distance from the star, distance from us.
from the star. I think it was from the star.
Okay.
Yeah. Okay, so Battle Bunny has a question for Jane. Can spectroscopy tell how the chemical makeup of the planet interacts with each other? In other words, are there periods of 51 Peg B's transit where there's more of a chemical in the atmosphere?
So we talked just very briefly earlier about differences between the day side and the night side chemistry, but I will pass that over to Remco because he knows much more about the chemistry of the atmospheres in terms of how they interact.
Yeah, so in principle, you expect there being differences, maybe not in carbon monoxide and water, but other species definitely. So because we think these planets are tidally locked and one side is always hot and the other side is always cool, you will have different chemistry taking place on one side from the other. But at the moment, nobody has yet detected really molecules on the night side. And at the moment, also, we don't really have enough signal to noise with the current measurements to do this at a very high level. but soon we will be able to do this. Yeah, we will look at differences in chemistry, and from this you can also derive things like wind speeds on the planets, which is also pretty cool.
Yeah, that is cool. Okay, so let's see. I think oh my goodness, we're almost out of time. Galaxy is asking, will there be searches or analysis of data for more planets in this system? Are we going to be looking for more anytime soon?
So 51 Peg B has been monitored in radial velocity for the last 21 years. And I actually went back and looked at all of that data to get a good solution for the orbit of 51 Peg B. What you could do is actually remove the signal of 51 Peg B from those data and then look deeper into that data to look for additional signals from other planets. And so there are several teams, not us, but other teams that are doing this, looking at they've been watching these systems for a very long time, and they're starting to dig in and look for additional signals. So nothing has been announced for 51 Peg, as far as I know for now.
Yeah.
But we have 20 years of data on it. So.
All right, one more question. I'm out of time, but I want to get this one in because it's a good one. Julia Lynn is asking, how's the method of obscuring the star coming along? What's the current hard limit in the minimum mechanical obstruction? Wouldn't this be the surest way to directly observe entire star systems? What she's talking about are things like star shades or things that you can, little occulters, things you can do to block out the star's light so that you can better see the planets themselves. Is this a possibility for your research on 51 Peg B in the future? Would that make your observations better to be able to block out the star?
So if you can block out the star, then you can just take this spectrum directly of the planet to look at then what's in its atmosphere, instead of having to use the velocity change or the spatial information. So I think, as I said before, 51 Peg B is about 100 times closer than the closest thing that we've seen to date. And I think we're still quite a way off from reaching sort of the milliarc second separation. But this is work that's being done. You talked about star shades. This is an idea that's being considered for the next great observatory that NASA will launch to replace Hubble and after JWST as well.
That's right. And there's also JWST will have, I'll just comment briefly, little micro shutters on NIRSpec that's the spectrometer that they're going to be using to actually block out the star's light. Do you guys have, what about that? Could you guys use JWST to maybe get some better observations of 51 Peg B?
Matteo, did you want to comment on that?
I would say spectral resolution is as we mentioned before, our analysis is really based on this ultra high spectral resolution, which means the spectral.
Oh, you got frozen.
I know. I can sort of try.
Maybe I can say something. Yeah.
Go ahead.
So for this direct imaging, it's the size of the telescope is very important. So JWST is smaller than, for instance, the Very Large Telescope. So it's
aperture's king in this.
Yeah.
Okay.
So that determines the resolution of your image.
All right.
So, So it's for definitely for 51 Peg B, it's not possible with JWST, but for in the future for Earth-like planets, for instance, around Sun-like stars, it's a good option for future space telescopes.
Okay, great. Thank you guys very much I'm going to have to cut it off here. We're out of time, folks. You guys had some great questions. Thank you for participating, and the chat box was just on fire today. So thank you very much for joining in and asking these great questions. You guys are awesome. I want to thank my guest, Dr. Jane Birkby. She's a NASA Sagan Fellow at Harvard Smithsonian Center for Astrophysics. Also, Dr. Remco Dukak. He's from the Netherlands Institute for Space Research, and Dr. Matteo Broggi. Did I get it right that time? Oh, he's gone. That's right.
He's back.
Oh, he's back.
Sorry, my laptop just crashed without any notice.
When it was all over. Okay, from the University of Colorado's Astronomy and Planetary Sciences Department. Thank you very much, guys, for joining us.
Yeah, thank you.
Thank you for sharing your paper and your research.
Thank you.
And we hope you'll come back and let us know what's new when you guys get some more results.
Absolutely.
Yeah. So thank you. Oh, and Carol. Thank you for setting all of this up. It's been another great hangout. You guys are all Excellent. Thank you for participating. Thank you all for watching, and we'll be back next week where we will be talking about. Oh, we have an Astro Coffee next week, don't we? Don't we, Carol?
Yes, we do. We have an extra Thursday in the month.
That's right. So we'll be back next week with another Astro Coffee. So we don't want to check that out. And do we know what it's about yet? I know. I should. Never mind. I will put
Probably.
you on the spot. Every Thursday, right here, 3 o'clock, we're doing something Eastern time. So check it out. We'll be talking next week with a new group.
Probably about something about black holes.
Probably. Okay, good. My favorite topic. Okay. Thank you all for watching. And as always, keep
Looking up.